Yeah, hello everyone. So today I'm giving, like in the program you may have seen, I'm giving two back-to-back talks. It is really one big talk, that's why I just made the title Robot Learning. But I tried to divide it such that it is like we start with some reinforcement learning and we continue with some imitation learning or inverse reinforcement learning. So the first part is going to be reinforcement learning, and this is a summer school on more focused on the AIxHRI applications. So it's going to be more like human in the loop reinforcement learning. Okay. So maybe before I start, okay, I'm not going to test your self-confidence, but if I say something like TD error, temporal difference error, is it a term familiar to you? Maybe raise your hand if it's familiar. Okay, that's like half of the room knows about it. Okay, good. So the way I'm going to do this is I'll start with some basics of reinforcement learning. Of course, like reinforcement learning is a huge topic. There are like semester-long classes on that. But I'll try to do a very quick introduction of what reinforcement learning is and what kind of algorithms there are. So it's going to be more like there are this family of algorithms, this family of algorithms, this family of algorithms. And then I'm going to start talking about how we can incorporate human feedback into reinforcement learning. Okay. So let's start with some basics and let's define the problem first. So in reinforcement learning, we are interested in these types of problems that we can formulate as a Markov decision process. Okay, so what is a Markov decision process? In a Markov decision process, we have a state space. You can think of it as like the states the world can be in, right? So this includes your robot, this includes the environment of the robot. If there are humans, this includes the humans. So this is everything about the environment. And then we are going to, we have a decision-making agent. In the robotics, this is usually a robot, but more broadly, it is any decision-making agent. And it's going to take some actions that come from the action space, capital A. And based on the actions this decision-making agent takes, the world is going to move to a new state. Okay, so we have this transition function, and in most cases, the more general cases, we model it as a stochastic function. So given a state and an action by the agent, we are going to move to a new state according to this distribution from the transition function. This is, of course, single-agent reinforcement learning. There are also multi-agent variants, but today we are interested in the single-agent version. Okay. And based on the action that we take, the agent is going to get some reward. So you can think of this as like if you do a good action, you get positive reward. If you get a bad action, it's a negative reward. And there's this thing called discount factor. This is sometimes people say this is for numerical stability, but in an infinite horizon MDP, you actually absolutely need this because the goal is to learn a policy that maximizes the sum of the rewards, like from now to the end of time, but this is infinite horizon, so there is no end of time. If you do not add the discount factor, this thing will diverge. So that's why we have this discount factor, and if you look at the objective here, it is sum of the discounted rewards. Right? So traditionally, reward used to be cost. The joke is that learning people are more optimistic than control theory people, so they decided to call it reward. And we are making some assumptions here, and these assumptions, these are very standard in reinforcement learning. People will not object if you talk about these assumptions, but it's good to be aware of those. One of them is we are assuming discrete time, so the time is moving with some discrete frequency. There are continuous versions. Things become much more uglier, you need to deal with differential equations in that case. But in reinforcement learning, we are interested in discrete time. And the other assumption we are making is rewards are additive. So you take one action now, you get some reward, you take another action, you get some reward. What you care about is the sum of those rewards. Okay. Now, how do we solve this problem? How do we come up with a policy? How do we maximize this objective with a policy? So one way to do this is to write this as a constrained optimization problem. So in the objective, we have the same thing. This is the expected sum of discounted rewards. And we have basically two constraints. One of them is that I have some environment dynamics. So when I take an action from a state, I'm going to move to a new state. Here I write it deterministically that W here is like a noise term. Okay, so the W itself is stochastic. So that's how I capture stochasticity. And then the second objective is that the actions are going to come from my policy. Okay. So if we can solve this constraint optimization problem, we solve reinforcement learning. Good. And indeed, like, this is a dynamic programming problem. So if you have everything here, like if you have the reward function, if you have a transition function, you can solve this with dynamic programming. Okay. But what if we don't know the transition function f? Like, what if we can interact with the environment, but we don't have a closed form transition function? Or the same thing for the reward function as well. Then comes reinforcement learning. And reinforcement learning, I'm going to divide this into two categories as model-based and model-free reinforcement learning. There are different, like, there are different taxonomies. You can also do on policy, off policy, offline, online. Here, I'm going to do this taxonomy, model-based and model-free. So the idea in model-based is that you first learn a model of the environment, and then you go with the standard solutions. As I said, like if you know the transition function, if you know the reward function, you can do the dynamic programming on this. So the idea in model-based is that you are first going to learn those unknown functions, like the transition function and reward function. And later, whatever you learned, you are going to assume that is the underlying model of the world, and you are just going to do dynamic programming. So that's the model-based reinforcement learning. Under model-free, there are still two categories. One of them is you can do approximate dynamic programming. So we can directly go for the objective, and I'm going to talk about how this is related to dynamic programming. Or we can do direct policy search, meaning I'm not going to try to learn the environment, like I'm not going to try to learn this transition function f or the reward function r. I will directly get the gradients for my policy, and I will go for policy, and that's called direct policy search. Now, very briefly, how do we do this? So in model-based RL, as I said, the idea is we are first going to learn a model, like a transition function or a reward function, and then we will do something like dynamic programming. So how do we do this? We are going to collect some data from the environment, meaning I will let the robot go in the environment with some policy. Ideally, it's a policy that also explores the world well. And it's going to collect this data that are like tuples of state. An action that the robot takes can be a random action. And then it moves to a new state and collects some reward R, right? So I'm going to collect a lot of data like this. And then I can just do supervised learning, right? So because if, for example, if the thing that I'm trying to learn is the reward function, it is going to be a function from like S and A to R. That's one way of defining the reward. Or if you are trying to learn the transition function, it is a function from S and A to the next S. So you can do supervised learning, and after you do supervised learning, now you have a rough model of the transition function, and you can use this learn function to approximately solve the problem. Of course, there's the exploration problem. So what people end up doing is you first collect some data, you learn a model. Using that model, you improve your policy. Using your new policy, you collect more data, improve your model further, improve your policy. So you do this thing in a loop. Okay. So yeah, that's the function that we are learning. So that is like a very quick overview of model-based RL. The other category that I talked about is direct policy search. And in direct policy search, the idea is to formulate it as an unconstrained optimization problem and to solve for pi. Okay. So pi is the policy. But of course, the set of policies are too large because, okay, how do you define a policy? A policy is a mapping from the state space to the action space, or from state space to the probability distributions over action space. That is a very large set. So we cannot really search over this entire policy space. Instead, what we do is we parameterize the policy. So you assume a functional form for the policy, and you then search over the space of that functional form. So think of it as like, I'm just going to assume my policy is a neural network with, let's say, 3 dense layers. And then all I need to do is to search over the parameters of these dense layers, right? So instead of searching over the entire policy space, I'm going to parameterize it with some data. And I'm going to search over, oh, it's not in the slides. I'm going to search over like pi subdata. Okay. So how do I write this as an unconstrained optimization problem? Well, I have an objective that says I'm trying to maximize the sum of rewards over the trajectory, right? So I'm going to abuse the notation a little bit. So here the objective is like I'm writing r tau. So tau is a trajectory, right? And r tau is the sum of discounted rewards of that trajectory. So that's what I'm trying to optimize. And I have an expectation there because the policy can be stochastic, the environment can be stochastic. So I'm trying to maximize this objective for some theta that parameterize the policy. So okay, that's my objective. And how do I write this? Well, this is an expectation, so I can just expand the expectation with an integral, right? And if I have an objective, one way to optimize this, and I guess the first way that we usually go for, is to compute its gradient and just move in the direction of the gradient to optimize it. So if I can write the gradient of this thing, then I can just move my policy with that gradient and it's going to maximize the objective, right? So how do I write the gradient? Well, gradient is linear, so I can just put it inside the integral. And then the reward function, this r tau here, it doesn't depend on theta, so I can just move it out. It is just the probability of trajectories or the distribution over trajectories that depends on theta, because theta produces theta is the policy that produces the trajectories. And here there is this little trick that we call a policy gradient trick. So we apply that, and the idea is instead of writing this as the gradient of a probability distribution, we are going to write it as, well, first we're going to like multiply and divide by the same term. And now look at here, what do I have here? It is the gradient of the log of the probability. Okay. So why is this useful? Because now I have this probability term here inside the integral, but it's outside the gradient. And I can again turn this into an expectation. Okay, so now this is where I am. And now I'm going to expand this term, this logarithm of the probability of the trajectory. So how do you write the probability of a trajectory? A trajectory is basically multiple state action, like state transitions, right? State action transitions that are like back to back. So the probability of a trajectory is the multiplication of each of these time steps. And here it's inside the logarithm. So I can actually write this as like logarithm, the probability of the first state, and then the probability that I take this action. And when I take that action, what is the probability that I move to the next state? And then I keep doing this over the entire trajectory. And because this whole thing is inside the logarithm, I can just write it as summations. And this whole thing is inside the gradient of theta. So I can actually drop all the terms that do not depend on theta. Like here, this is the distribution over the initial state. It has nothing to do with theta. It is a property of the environment. So that will go. And then this one, like state action moves to the next state. So this is just a transition function. It has nothing to do with the policy, right? So this will go. It is only this last term that will remain. And again, I can put the gradient inside the summation. And now the nice thing is, if you remember, I said we cannot search over the entire policy space, but we can parameterize the policy space and we can do the search over those parameters. And this last term here, it is like, this is a functional form that we assume, something like a neural network, right? So I give my neural network a state, it gives an action, it gives a like distribution over actions. I can take the logarithm of the action that I take, and now this is the gradient. So it's a neural network. I can compute the gradients. So I actually, now this is a term that I can compute as opposed to the probability, as opposed to the gradient over the probability of the trajectory. So then I have this as my final gradient. And there's also this nice causality relation, like it reduces the variance. So you actually see that if you go from here to here, it's the same. So what is the difference? This is just saying that this inner summation, you can actually start from the current time step of the outer summation because the previous actions do not depend on the future states. Right? So when you do this, now you have this gradient, and this is called the reinforced algorithm, or it's also known as policy gradient, because at the end what we achieve is we have this gradient of the objective, and we are just going to move the policy in this direction, and at every step the policy is going to get better and better. Okay. So this is direct policy search. And finally, there is approximate dynamic programming, where the idea is, okay, I don't know how familiar you are with dynamic programming, but there's this thing called Bellman equation. And in Bellman equation, the idea is you define this thing called Q function, or state action value function. And it is like you can think of it as like I am in some state S, I have some policy pi. Starting from this state, if I follow this policy, what is my expected sum of discounted rewards to the future? Right? So that's Q, but it has two inputs. It has state and action. So it is not just following the policy. Instead, it is like I'm at state S. I'm going to take action A. So my first action is given by the function input. And after that, I'm going to follow pi. Okay, so that's the state action value function. And how do you define this? Well, initially, your initial action is given by the input, right? So initially, this is the reward that you are going to get. That's like guaranteed. And after that, you are going to follow a policy. So in the case of an optimal policy, this would be just a maximization over the next Q function. Right? Because when you start from state S and you take an action A, you go to state S prime. And from this S prime, if you're trying to find the optimal Q function, the next best thing you can do is to take the action that will maximize the Q function at this new state. And then from the next state, you do the same thing. From the next state, you do the same thing. Right? So it gives us this nice recursive equation. And this is like the backbone of dynamic programming. And the idea in approximate dynamic programming is to collect some data from the environment and directly go for this Q function. So the nice property of Bellman equation is for an optimal policy, or I mean for any policy, this is unique. Right? And that includes optimal policy. So we have this unique recursive relation. And what this means is I can start with an arbitrary Q function. And I will do this iterative process where like I start with some arbitrary Q function. I will collect some data from the environment. I'm going to try to fit my data, like fit a new Q function based on that data. And I'm going to keep doing this. Eventually, when the fit is perfect, I know that it is the optimal Q function because Bellman equation is unique. So like as an algorithm, what does it look like? It is like this. So as I said, initially you start with some arbitrary Q function. Let's say you assume for every state action pair, all Q values are 0, like something like this, right? Something as arbitrary or as simple as that. Okay, and then you are going to collect some data, meaning some like state, action, reward, next state, next action kind of data. And you are going to say, now I'm at this state S, and in my data, I took this action A to go from here to here. So initially, based on my initial arbitrary Q function, the Q value here of the next state was 0. But now, based on the data, I see that moving from here to here gave me a reward of 2. So now I'm going to say that the Q function, the Q value of this state is 2. Okay. So you do this once, right? Now in the, let's say the next iteration, now you are already here. And you can think of it as like based on my, again, initial Q function, the next state, the Q value is 0. But from here to here, I get a reward of -1. Oh, so the Q function of Q value of this state is actually -1. And then in the next iteration, it's going to make it such that here it wasn't actually 2, it was 1, because it was 2 and then -1 here, right? So iteratively, it will correct your Q function And with this recursion, we are going to get better and better queue functions. Another way to think of this, or this actually, when I was first learning this, my intuition got better when I start thinking of this way. So you have an initial queue function that is arbitrary, so it has no information about the environment, right? And you are trying to improve this. Now, let's look at this equation here, this one. Right? Now, on the right, let's say it's my old queue function, and on the left is the new one that I'm updating. So instead of the approximate equal equation, assume it's an assignment. Right? Now, is my, let's say, here on the left, if I use my initial Q estimate for estimating the value of Q at SA, is it a better approximation of the true value, or is the right-hand side a better approximation of the Q value? So in one case, on the left-hand side, they tell me this is the state, this is the action, what is the Q value? I only have my arbitrary initial Q, right? So it has no information about the environment. So it's not going to be a good estimate. On the right, what I have is, I have some reward signal from the environment, plus this maximization, but again, it's from the initial arbitrary Q function. So after the plus sign, again, non-informative. But still, the right-hand side is better because there is some signal from the environment, right? There's the reward function. So that's why, like, if you think of this approximate equal sign as an assignment, the right-hand side is a better approximation of the Q function than the left-hand side, and that's why, like, we are assigning it as the naive Q function. Right? And you keep doing this, so over time your Q function improves. And indeed, this is how the SARSA algorithm works. The idea is you decide some learning rate kind of term, like this nu, right? And then you keep some of the old, you give some weight to the old Q function. And with the data that you just collected, you update the old Q function to get the new Q function. It's called SARSA because it's like state, action, reward, next state, next action. So it's like a little abbreviation. Okay. And this last equation here, we can actually rewrite it. So we can group the terms that have a multiplication of nu. And this is what you get. So on the left-hand side is the new Q function. You have the old Q function. You correct the old Q function with some error term. And this is a temporal difference error. So this is TD error. Right? So this is, you have some reward plus the old Q function. So the first two terms inside the parentheses is your better estimate. And this is your worse estimate. So the difference between them is the error. So you update your old Q function with the error. Okay. Any questions so far about this little quick taxonomy that I tried to make? Okay. And this is one of the cases where I don't know if no questions is a good sign or a bad sign. I'm going to give 5 more seconds in case you are thinking of a question and you are too shy to ask. Half of the room doesn't know reinforcement learning, so no question is going to be a bad question. Okay? Okay. Now, this is like, one thing you may notice is in all these algorithms, like I was saying, for example, in the model-based reinforcement learning, you first learn a model, like the transition function or the reward function, and you use dynamic programming. Or here, we have this maximization over the action space, right? But what if it is a continuous problem? Like, what if the action space is continuous? Indeed, in most of the robotics applications, it's going to be a continuous action space. One nice solution is there are actor-critic methods. So this is not something that's outside of the taxonomy, but I'm presenting this as a separate thing because they're particularly useful when the action space is continuous. So the idea is, like here in approximate dynamic programming, what we end up learning is this Q function, right? And given the Q function, how do you decide what action to take? Well, you just find an action that maximizes the Q value, the Q function, and you just follow that as like your policy. But what I'm saying is at every time step, you are going to compute this QSA for all different possibilities of A, for all different possible actions, and whichever is the highest, you are going to take that. If it's a continuous action space, you can actually do that. So the idea in actor-critic is to learn that optimization too. So the Q function, in actor-critic methods, they call it a critic, because for any state, given an action, it criticizes how good that action is. Right? And then there is the separate, let's say, again, a neural network. It doesn't have to be a neural network, but nowadays it's usually a neural network. That's called actor. And the goal of the actor is to produce actions that will maximize the value from the critic. Okay? So the Q learning that I talked about is giving us the critic, and then there's this actor that tries to maximize the critic. And that's actor-critic, and there are like a bunch of methods that try to do that. Indeed, like if you use reinforcement learning in your projects, like if you are not developing reinforcement learning algorithms, but if you are using reinforcement learning in your algorithms, usually one of the first things you try is either the PPO or SAC algorithm, because they're pretty good. And they're actually both actor-critic methods. PPO, you can do it non-actor-critic, but both of them are usually have the actor-critic architecture. Okay. Oops. So, oh, there's a question. Yes.
This kind of actor-critic method, it's kind of a brute force method, like the actor just tried actions and evaluate them to see which one is best for function.
Yeah, good question. So it's not necessarily brute force. It is still an optimization. So you can think of it as like policy gradient, right? In the policy gradient that I talked about, we wrote an unconstrained optimization problem, and we said we are going to update the parameters of the policy to maximize this sum of rewards. Like, think of the exact same procedure, but now instead of the sum of rewards there, you have the Q function from the critic. And so it is indeed like it needs to try different actions because it is solving an optimization, but it is not like I'm going to try to cover the action space as much as possible and try to find the best action. Instead, it has this nice like policy gradient kind of optimization where like the actor starts with some randomly initialized neural network. So initially it's going to take bad actions, but every time it takes an action, it will get this policy gradient, and over time it's going to get better and better. So it is it's much better than brute force. Any other question? Okay. So everything I described so far, as I said, these are like some basics of reinforcement learning. I tried to give a taxonomy that kind of summarizes the different categories of reinforcement learning algorithms. But the point of today's talk is more like human-in-the-loop reinforcement learning, or reinforcement learning where there's some human feedback. And when we look at this problem formulation, there is no human here, right? So where is the human? One way we can generalize this problem is instead of an MDP, we can make it a partial observable MDP, or it's called POMDP. The idea is in most of the realistic applications, again, especially in robotics, the robot actually doesn't get to observe everything, right? So like here, when I define state, I said it's going to include everything about the environment. Like it's going to include everything that's happening in this room, like everything, like the people, like let's say if there are people around, all their movements, all their intentions, everything that will define the next state. Right? But in reality, our robots have sensors, and whatever the sensors give them, that's what they see. Right? And in most cases, you cannot observe everything. I mean, even as humans, we are not really observing everything. So the more realistic formulation is partial observable MDP. The idea is so the left-hand side is the same, right? Except now your policy is defined over the observations instead of states. And what are the observations? Observations is this other set, and they come from the states. So given a state, your robot has some observations. Think of it as like there is a true state of the environment, but if the robot has a grayscale camera, it doesn't see color, right? So now color is part of the state, but it's not part of the observation. And now we are trying to learn a policy that will operate the robot over the observations. So this actually breaks all the, like from a theoretical point of view, this breaks the reinforcement learning algorithms, but in practice it works. So that's why like this is fine. So when you look at reinforcement learning papers that do robotics applications, often what you'll see is they'll say, we use the like camera image of the robot as the state of the environment. Well, it's not really the state because it doesn't have the Markovian property, but because it works, we go with it. Okay. So now there are different ways humans can be involved in this. First of all, they can be part of the state, right? So they can be in the environment and maybe they're collaborating with the robot, maybe they're competing against the robot, maybe they just coexist. So that's one way. But this lecture is more on learning from human feedback. So I'm going to talk about the cases where the human is trying to contribute to the learning of the robot. And one way this can happen is the human may contribute to what the robot observes. So the robot is seeing some things and the human can inject some information there in different ways. And based on this, the robot learn better. So one interesting project that we did in this direction was this learning from eye gaze, right? So I'm going to do a quick like demonstration of this, or not a demonstration, but like a little quick experiment, let's say. So I'm going to show you this one simulation video from MetaWorld, and I just want you to watch the video. Like the robot is going to just open the drawer, and it's a 9-second video that I want you to watch. Okay. Now, oops. I should have blacked out the screen because I was going to ask, did the robot have a shadow? Because in most cases, people cannot answer because they were not paying attention to the shadow. Like, why do you care if the robot has a shadow? Robot or the task the robot is trying to complete. So in this case, like opening the drawer. So you just look at the end effector and you look at the handle of the drawer, right? But that's not what our robots are doing. Like if you think of the reinforcement learning loop, this is what the robot does. There is an observation, like let's say the image of the environment. It goes to the robot's policy. The robot takes an action, it gets a reward, and this loop continues. Right? So the robot doesn't know where to look at. It is just this entire image that it's looking at. The hope is that if you train it enough, eventually, like it will learn what matters. Right? So one idea where like humans can be involved is maybe as humans we can tell the robot this part is important, this part is important, this part is not important, right? So we can add this extra observation to the robot. So at every frame we can say here in this observation, in this frame, this region is important, you can ignore the rest. So I can make this like addition to the robot's observation. So we tried this on this little interface where like the user was basically using their mouse to click on what is important in the frame and what is not important. Well, mostly what is important and everything else is not important. And we were creating this heat map based on how long the user hover around that region. So now the idea is we are going to put a human in the loop, and for every observation, the human is going to annotate it, and we are going to give it together to the robot. So we are adding an extra observation to the robot. Of course, this is way too expensive because like we cannot annotate every frame. Luckily, computer vision people solved it for us. It is like there are these papers that predict attention or saliency. So there are some pre-trained models, you just fine-tune them and they tell you what the human would look at or what is important in that task. So we just fine-tuned one such model. I think it's called Picanet in this case. And then we trained the reinforcement learning algorithm. So here, like what we are doing is really simple. So a CNN is a convolutional neural network. So we are just adding the salience, the attention of the human, as an additional channel. So you have the RGB image, right? Now it is like RGBS, so you have the saliency. Like as simple as that. We just add this extra observation, and with this extra observation, the robot was actually learning faster. Another thing you can do is you can actually use this for representation learning. So if the human is giving some extra observations, you can use this to learn a better representation. So in this case, what we did was there are the default observations. So in this case, the RGB image. There are the human contributed observations. And we created this transformer encoder such that we encode both of them in a way that using the RGB, we try to reconstruct the humans edition, or using the humans edition, we try to reconstruct the RGB image. So it's like, it's called multimodal masked autoencoder. And using those representations, we get some like embedding of the observation, and we use that embedding to do representation learning, reinforcement learning, and that also improves the sample efficiency of the robot. So in a way, in this specific case, we were telling robot what is important and what is not, but more broadly, you can think of this as like the human is contributing some observations to the robot with the purpose of teaching the robot, and you can use this to learn better representations. And the same thing holds for imitation learning, but I didn't talk about it yet. And then we were wondering if we can obtain salience more easily, and indeed yes, because humans have eyes and they look at the important parts of the task, the important parts of the scene. So we started recording their eye gaze. Here is like one little AIxHRI experiment that we did. If you see the red dot, it is not my mouse. It's the eye gaze. Oh, sorry, there's a second red dot. Oops. This one is my mouse. Okay. Now my mouse is out of the screen. So it is the human eye gaze, and you'll see that the human is usually looking at the enemies that it needs to shoot, and sometimes it looks at the submarine. I think it's good for localization. But this was like a little preliminary study that we did to make sure there is indeed like good correlation between the task saliency and the human's attention. And then we started collecting data with these Meta's Aria glasses. So this is the eyes of my master student. Yeah, it looks interesting from this perspective, but that's the data. And here, like, I asked him to do some, house chores with the glasses on, and he's like cutting a paper, or he's folding some clothes, and we again see the eye gaze annotated, and again you'll see that it correlates nicely with the task. Okay. And in general, eye gaze is something that I'm very excited about, because in most cases, when we are collecting data from humans, or when we are doing reinforcement learning and there is a human like just observing the scene, eye gaze is always there. Like you don't need to put any effort because you're already looking at the thing. Like we just need to record it, and when we record it, it turns out it improves data efficiency. And then instead of doing representation learning, we said, how about we regularize the policy, this reinforcement learning policy or imitation learning policy, such that its attention matches what the human is looking at, right? So there is this like additional loss function, it's like supervised loss, right? We have the attention layers, or we have the attention from a CNN, and we are going to regularize it such that if the human is looking at a region, I want the attention of that region to be higher than the rest. So we collected some more data, like using this Clara driving, and it's all open source. Like we have this data with people playing AIxHRI games. 2 of my students became experts on AIxHRI after this project. And then they were also like doing this driving simulator. It's called Gabriel. It's, as I said, the whole thing is open source, the data, the code, everything. As with any large table, the summary is that our method works great. But more interesting, I think, visuals is that we get better generalization when we have eye gaze, because the policy actually learns where to look at. So here on the right-hand side, it is just behavioral cloning. So this is just doing supervised learning without any eye gaze or something. And I particularly like this video on the bottom right, because so what we are seeing here is what the policy is paying attention to, and it's paying attention to the trees on the right because it just memorized the route, and based on where the trees are, it can drive. But if you look at the third column, that is the gaze regularized one, it actually looks at like the bikers, pedestrians, other cars around. So it's we can say it is doing something more proper. But yeah, contributing to the observations of the robot is one way that humans can be involved. But more generally, and most of the work in this like human-in-the-loop reinforcement learning or learning from human feedback, it focuses on the reward function. So like humans may contribute to observations indeed, but there is much more work where the human is contributing to the reward function, because like so far, when I was talking about reinforcement learning, I was assuming there is this thing called reward function, and it's kind of given, right? Maybe not in a closed form, but when the robot takes an action, there is this authority somewhere that tells that was good +2 or that was bad -2, right? But where does this reward come from? So sometimes it's given, and indeed, if you look at the old reinforcement learning, I mean old as like not so old, but nowadays it would be called old because this is like 2017. If you look at those reinforcement learning algorithms where neural networks plus reinforcement learning became successful for the first time, they were looking at these kind of Atari games. And in Atari games, there is indeed a reward function. Like there is this score that you are trying to maximize. So it can be given in that case. But what if we are trying to do something like autonomous driving, right? Like what is a good function for an autonomous car? So let's say, yeah, let's do this interactive. So let's say I have this little game where I want this car to drive autonomously, and I want it to reach some other point somewhere. So like, what would be the reward function? This is a problem that companies couldn't solve for 20 years, and now I'm asking you to tell me something in 5 seconds. So there is no good. Reaching the destination. Okay, so then the reward function, would it look like something like if you're at the destination +1, otherwise 0? Is that reasonable? Right. I mean, it is reasonable. The problem is it is very sparse. Like for reinforcement learning, you usually want to give rewards at every time step, because otherwise, for the robot to learn anything, it will need to reach the destination at least once, and it's difficult to do without getting any feedback. So it is indeed the true reward function, but it's not going to make it possible to do it, learn it with reinforcement learning.
All the driving laws, whether the trajectory is smooth,
okay.
like, yeah, follow traffic rules.
Yeah. So you can try to add all the traffic rules, and for every, I mean, there's the difficulty of like detecting the violations, but for every violation you give some negative reward, right? Yeah, that would work. I mean, you still need to add something about the destination because we want to go to a destination. Yeah, that's a good one. Any other here? Moving forward to the destination. So yes, like something like progress towards like getting close to the destination. As you get close, you get higher reward. Yeah, that's a good one. Yeah.
Maybe adapting to the path or adapting to the route.
So is it like something like lane following, like staying within the, yeah, that's also a good one. So we can like add all these like individual components, and we can try to come up with a reward function, and later we are going to try to do reinforcement learning. And I think like with all these, like adding all the traffic rules, adding comfort, adding a reward based on like staying in the lane or getting close to destination, I think it will work as long as there are no other pedestrians or cars or bikers around, right? But like here the point is about like how to design the reward function. So maybe like we can propose something like negative reward for crashing or violating traffic rules, something like that, and then maybe some positive reward for high speed, but negative reward for too high speed, because that's also a part of the rules. So we can do something like this, and indeed like this is a little experiment that somebody did, and I really like the result. So they coded this reward function and they did reinforcement learning, and this is what the car learned. Because it is like you have some speed, it's not too high, and well, you are moving forward, you are not crashing anything, so good job. Right, so the point is designing reward functions is difficult. Here's another one. Like, what is a good reward function for a robot vacuum? To do all the space, yeah, you can just go everywhere, right? Let's say we want to train it in a way that it prioritizes the places that are dirty more often, right? Why not? Okay, I'll show this one. So here is the proposal. So positive for vacuuming dirt, right? It just, if it gets dirt, positive, otherwise negative. And then this is an exempt from the foundations of the artificial intelligence book. And it says that if you do this, what the robot can do is it can just collect some dirt, it can just empty it again, collect it again, empty it again, collect it again, right? Just like the car is doing the loop, the robot can do that. I have one final example. This is real. So this is this little Mojoko gym environment fetch push. The idea is on the table there is this little cube, and the task is to push the cube toward the goal. Right? And they thought, okay, it would be good to just do a reward function that is negative for error distance. So if you are far from the goal, some negative rewards. As you get closer, it's positive reward. Like, this is the default thing everybody would do, right? Then there are these GitHub issues that people started, and they say, like, when I'm training this reinforcement learning algorithm on Hucebot 0, the agent sometimes learns to push the big block to achieve its goal. So instead of moving the little cube, it was moving the entire table, right? And then this other person is saying the same thing. They say, like, it is funny, it's fun, but it's not the expected behavior. So designing reward functions is difficult, and the humans can provide rewards. So instead of, like, we trying to write a reward function, we could make it such that at every time step, human observes it and says, this was good, this was bad, right? And this was the idea behind this old, like, paper called Tamer, Tamer. Oh, it's on the bottom. So it was exactly this. Like, the robot is interacting with the environment. Every time the human like watches what happens, and at every time step they say positive reward, negative reward, positive reward, negative reward. Of course, this is too much work, because if you work with reinforcement learning, you know that, like, we are talking about millions of time steps here, and we don't want humans to give, like, millions of plus minus rewards. But if you look at the applications of reinforcement learning, we see success stories like this. And this is from, like, 15, 16 years ago. This is at Stanford, and they were able to train this RC helicopter, or I guess, RC helicopter, using reinforcement learning, and it learned to do maneuvers. I think it's going to zoom in again, and we are going to see the helicopter doing some interesting. Yeah, apparently there are names of these maneuvers. I have no idea, but, like, it's doing a snap roll, split S, and this was all, like, learned with reinforcement learning. So that was quite cool. Right. Okay, it's a long video. It does a lot of maneuvers, so I'm going to skip it. And then I was thinking, okay, what would be a reward function for this? Maybe, like, you get some positive reward for maneuvers and negative reward for crashing. Well, it's not that easy. Because in that paper too, what they did is they learned it from expert demonstrations. And that is actually the most common way humans are involved in this entire reinforcement learning scheme, where, like, instead of we trying to design a reward function, we say, how about, as a human, I first control the system, right? And based on my expert demonstrations, we learn a reward function, and then we make the reinforcement learning optimize that learned reward function. Okay. So that's the idea in learning from demonstrations. And for this, we usually talk about imitation learning or inverse reinforcement learning. Unfortunately, there is no, like, unified, there's no agreement on what is inverse reinforcement learning, what is imitation learning. But I think the most common way people think about it is, like, imitation learning, you directly learn a policy. So there are some expert demonstrations, you directly go for the policy. In inverse reinforcement learning, again, there are some expert demonstrations. You first learn a reward function, and using that reward function, you learn a policy via reinforcement learning. Okay? And in terms of properties, imitation learning, it's simple, it's not ambiguous, and it is fast because you are just doing supervised learning. You are just trying to imitate the human's control. The inverse reinforcement learning, it is more difficult, but it's interpretable and generalizable because at the end you have both a reward function and a policy. And looking at the reward function, you can often tell why the robot or why the policy did what it did, right? So, it's also generalizable because once you have the reward function, now if the environment changes a little bit, like not the dynamics, but let's say you start from a different state, you can use the same reward function and still solve the environment with another like reinforcement learning loop. And inverse reinforcement learning has like has a long history. So it starts from like the Kalman filter in 1964, and later there is the multidimensional version of it, like the matrix version of this. And then the MDP formulation is at 2000. And then there are some like inverse reinforcement learning algorithms, like there's the future matching, maximum margin planning, and maximum entropy inverse reinforcement learning. And 2008 is really like this maximum entropy inverse reinforcement learning is kind of still the state of the art. I'm not saying that there are not new methods. There are like the generative adversarial methods, and now increasingly over the last, I would say, 1 or 2 years, people are going for methods where they learn a reward function in a completely supervised way. And with enough data, it scales well, so it works well. But in terms of, I would say, the foundations, or in terms of the methods that are not just data scaling, like this 2008 maximum entropy inverse reinforcement learning, I would say it's still the state of the art. And it has a long derivation, and it's in the slides. Will they have access to slides like after the summer school? Okay, cool. In the slides, I give the full derivation because if you look at the paper itself, it's actually kind of complicated, but I've been teaching about this in my class, so I decided it's a good idea to include the derivation. So it's in the slides. I'm not going to go over the entire derivation here because there's not enough time, but what I'm going to do is I'm going to try to give you an intuition of what it's trying to do. So in the general inverse reinforcement learning formulation, the idea is like you are trying to learn this reward function, right? And you formulate this as some, let's say, linear function of some features. Okay? So the features can be nonlinear. So in that way, this is still super general. And the idea is, let's say I already have some featurization. Maybe like I do some like autoencoders, or I have some features that I care about, so I encode them. And now I need to only learn this linear reward function weights. So this is, of course, a simplification. In modern approach, we don't do this linear reward thing. We just do neural network. But it's good for understanding the math behind it. Okay. And then what I can do is, so similar to the state action value function that I was talking about in reinforcement learning, the Q function, there's also the state value function, V function. So in state action value function, we said, I'm in this state, I'm going to take this action. What is going to be my future rewards from this, right? After this specific action. In the state value function, the V function, the first action is not given. So everything depends on the policy, starting from the first state, right? So that's the difference. And I can write this value function as like sum of discounted rewards. And if I replace the reward function as like W times the futures, W will go all the way out. And now inside this expectation, I have the sum of discounted futures. Now, why am I talking about this? Because we know that, like, again, this is from the Bellman equation, we know that the value of the optimal policy has to be no less than value of any other policy because it's the optimal policy. And I can write this as this linear equation, right? Sorry, linear inequality. And this is the only condition my W must satisfy, right? So I have these expert demonstrations that will be the left-hand side of the inequality. And then for any other policy, I want this inequality to be true. So because I assume that the expert demonstrations, they're experts, so they're optimal. So I need to find a W that will make this inequality correct for any given pi. right? The expert demonstrates on the left. Do you see any problem with this? Yeah.
Just in case there's noise in the demonstrations or there's
Yeah.
demonstrators of different levels of experience.
Yeah, that is one problem. Like, so the general IRL formulation, it assumes that all the demonstrations are expert, right? Like, there cannot be anything better than the human controlling the robot. In general, this is not true. Like, in simple problems, you can guarantee that, but in general, this is not true. So in practice, when we do this, when we write this optimization, we actually do not put this as a hard constraint. Instead, we add like a slack variable there, and we try to give some like room for error on the human. What else? That's one problem. There's another one.
Yeah, very sparse. Like you have this on just on the state and actions of the. It's not defined everywhere.
I'm not sure if I follow. Like, how is it? Why is it very sparse?
Policy star is defined only on the very sparse trajectories provided by the experts. It's not defined everywhere.
Right. Okay. Yeah. So if you are working with a small number of expert demonstrations, now you don't have enough constraints, and what it means is there can be multiple different W that will make all these inequalities true. I'm saying all these inequalities because this needs to be for all the states and for all the policies pi. But still, with a small number of expert demonstrations, there will be multiple W that will make this inequality correct. And related to this, actually the answer that I was expecting was you can just write W equals 0 and all the inequalities will be satisfied, right? So you just solve the inverse reinforcement learning. But the problem is this last issue that we just talked about. It's called reward ambiguity. So more generally, it's not just W equals 0. Like regardless of how many expert demonstrations you have, there will always be multiple W's that satisfy those inequalities. Okay, and this is called the reward ambiguity problem. I mean, if you have infinitely many W's, infinitely many expert demonstrations, that's a different story, but in practice that will never happen. So there will always be multiple different W's that will satisfy the inequalities. And the issue is, let's say you have like 100 demonstrations or 100,000 demonstrations. The different W's you will learn, excuse me, they will behave differently in some states, and those little differences in the behavior may actually make the policy suboptimal. Right? And yeah, the reward ambiguity is not just about scaling of the W. It's also about, as I said, with finite number of demonstrations, you can have different W's. So the idea in maximum entropy inverse reinforcement learning is to use this principle of maximum entropy, and that's where the name comes from. So what is the principle of maximum entropy? So we say instead of, maybe I should start with this actually. Yeah. So the assumption is that we're going to say experts are noisily optimal, right? So the probability of the expert gives a demonstration psi is equal to the like exponential of that trajectory's reward divided by the integration over the entire set of trajectories, right? So this is a softmax, or this is also called the Boltzmann model. The idea is if a trajectory has higher reward, the expert is more likely to give that. But if a trajectory has lower reward, it is still not zero probability, right? So we are giving some like wiggle room to the experts, so they can also give suboptimal demonstrations. Okay. And the key insight in maximum entropy inverse reinforcement learning is we are going to find a probability distribution over trajectories such that the future expectation matches the expert features. Okay. Because we define these features over the trajectories, right? So if the features of the policy that I come up with, if it matches the features of the expert, I know that the rewards of them are going to be the same. So it's not necessarily like I generate the same trajectories. I need to generate the same futures. But then the question is, okay, which distribution? Because there can be multiple such probability distributions. So this is the same problem as the reward ambiguity, right? Just like how there can be different reward functions that satisfy all the inequalities, there can be multiple probability distributions that will make this future match. So that's where the principle of maximum entropy comes in. And what this principle of maximum entropy says, I need to get some water, sorry. Okay. So what this principle of maximum entropy says is when you are trying to learn a distribution or where you are trying to find a distribution, if there are multiple distributions that like satisfy the conditions that you have, it says go for the one that leaves you the largest remaining uncertainty consistent with your constraints, right? So you are trying to learn a probability distribution, there are some constraints. What this says is maximize the uncertainty under your constraints so that you are not making any constraints that was not in your problem. Right? So how do we maximize uncertainty? We maximize the entropy. So it's an information theoretic term that if you maximize the entropy of a probability distribution, you are maximizing its uncertainty. Right? So to not introduce any like arbitrary constraints that was not part of the problem, this is what you are doing. So you maximize the entropy of the distribution that you are learning subject to these constraints. So here the constraints are you are trying to match the features of the expert, and you need your probability distribution to be a proper probability distribution. Okay, so as I said, I have the full derivation in the slides. So if you can follow this thing, and it goes like step by step. You write the Lagrangian and you solve the whole thing. I'm not going to do it here, but it should be like I didn't skip any steps, so it should be fine. Okay, and at the end, this gives an algorithm where the idea is you initialize some reward function W. Using that reward function, you do reinforcement learning and you learn a policy. And then using that policy, you again, you roll out the policy, and then you compute a new W and you repeat from the reinforcement learning step. Right. So of course, like, yes?
How do you quantify your uncertainty?
Oh, the quantification of uncertainty is this thing called entropy. So the idea is here, like we have this objective here, right? So this is, okay, maybe I should go a little back. There is this term called surprise, and this is not like this, as a mathematical term. There is this thing called surprise. So the idea is, let's say you are doing you are tossing a coin, right? If it's a fair coin, 50%, 50%. What is the logarithm, like, let's say, base 2 of like 1 divided by 2? It is like -1, so you just multiply with -1. So it is 1. So you say the surprise of getting heads from a coin toss is 1. The tails is the same. Now let's say the coin is not fair and it is 90% heads, 10% tails. What is the surprise if it is heads, the 90% one? Now you look at the log 2 of 0.9, again with the minus sign, it's going to be a smaller number, right? It's going to be smaller to 0, because indeed there's not much surprise. You are already expecting it to be heads because it's 90%, right? Versus what is the surprise if it is tails, which is the 10% one. So it is minus log 2 0.1, which is a higher number. So the entropy is expected surprise, right? So with 90% probability, I'm getting low surprise. With 10% probability, I'm getting high surprise. So in a coin toss, the highest uncertainty you can get is from a fair coin, right? But so this is here we are of course dealing with continuous, but this is exactly what I'm talking about, right? Like the log probability, this is surprise with the minus sign, and this makes it an expectation. So this is the expected surprise of the probability distribution. And that is a quantification of uncertainty. So higher the entropy, higher the uncertainty. Okay. Does it make sense? Any other question? Okay, yeah, as I said, with this maximum entropy inverse reinforcement learning approach, we get this nice algorithm. Nice in the sense that it is clean, it has like a nice mathematical background. But the problem is, to do inverse reinforcement learning once, we need to do reinforcement learning at every step, right? So that's why, like as I said, nowadays people are going for more supervised learning approach, where like if you have some expert demonstrations, they say things like, okay, I'm going to get an expert demonstration. The initial frame, I'm going to say this is 0 reward. The final state, this is like 1 reward, and I'm just going to interpolate. I'm going to do supervised learning over this. It is computationally much more efficient, but in terms of the foundations and in terms of doing it in a more rigorous way, maximum entropy inverse reinforcement learning is still the state of the art. So I'll continue with some like alternatives to learning from demonstrations, because demonstrations is just one type of feedback that we can get from humans. But there are many other types. There are like preferences, interventions. I already talked about eye gaze, or we can ask the humans to give their own demonstrations, like with their own hands. So I'm going to talk about a few different methods around those, but let's do it after the break, because I think this is the time for break.